Okay, so today we're going to talk about, at least start the hypothesis testing concepts. So I'm going to spend more time discussing the concept of hypothesis testing today before we start doing some problem solving, because it is really important for us to have a good grasp of the concepts that are introduced in this chapter, especially the five-step hypothesis testing procedure, because that is, again, it's critical, as I said earlier, that the concepts that you will see here are used in the succeeding chapters from here on until the end of the term. So, for this particular chapter, this is really nothing new, in the sense that we've already started talking about this concept of inferential statistics as early as in chapter 8, when we talked about computing probabilities of sample means being at least or as great as some number. And then we followed that understanding of probabilities in chapter 9, when we started talking about confidence interval estimation. So in chapter 9, we focused on this concept of interval estimation for an unknown population parameter, such as the population mean or the population proportion, or later on in next chapters when we talk about maybe the use of the F distribution in computing the confidence interval for a population standard deviation or population variance. So essentially, the one sample tests of hypothesis is an extension of this concept of interval estimation. Okay, so if we go back to kind of do a recall of what we covered in chapter 9. So here's a recap of chapter 9, where I used this flowchart for determining the appropriate way of computing, confidence interval for the mean or for the proportion using this flowchart. So if we simply replace this, instead of saying confidence interval estimation, we can replace this with term 1 population hypothesis test. Hypothesis testing, where in the previous chapter, we said that these were unknown numbers, but we wished to estimate them, all right? And we used to estimate them, for example, mu, we used x bar as its point estimate. And then for population proportion, we used the sample proportion as its point estimate. And then when we added the margin of error to each one of these, we computed what we know as the confidence interval estimate. So we will apply this same flow chart to chapter 10. Okay, are we clear so far? Okay, let me, once you if you've downloaded the PowerPoint slide for chapter 10. So some of the slides that I would say that are important for you to focus on when you are reviewing or studying chapter 10 would be slide number 3. Okay, so I'm just going to point this out to you, and then some of this I will be using today. So slide number 3, slide number 4, slide number 5, okay, slide number 6, that's important, and then slide number 7, we'll be talking about the difference between a one-tail versus two-tail tests. And this is a particularly important slide because this will be a useful guide when you are doing some actual problem solving. Because here I summarize important tips, or at least important keywords for you to pay attention to when you are reading or when you are doing problem solving. Okay. And then this one is an important slide also because this gives you guidelines for how to set up hypotheses involving the mean, if you were testing for the mean of a population. All right. And another slide.
Could I just ask you a quick question?
Sure.
I just downloaded the PowerPoint from the Moodle site, and it looks like the page numbers are slightly off. Could we maybe have a different version?
Probably, but I will post this this new one.
Okay.
Okay. But it's pretty close to maybe off by one slide number. Okay. So this is another one, setting up hypotheses for testing a population proportion. Here's an important one. Okay, this is in relation to studying one-tailed versus two-tailed tests. And then another important slide is this slide here, number 30. Okay, because this one talks about the interpretation of the p-value when we compare that to a significance level. All right, so now that I've just identified those important slides, I will refer to them again as I discuss more in detail the concepts involved in hypothesis testing. All right, so let's start by talking about what hypothesis testing is about. All right, so a hypothesis or hypothesis testing is defined as a procedure that is based on sample evidence. So we've seen this in chapter 9, where we used sample n, so that the sample is our evidence, and it is also based on probability theory. So as I said in chapter 8, we talked about obtaining probabilities for x bar to determine whether the hypothesis is a reasonable statement. Okay, so the question is, what is a hypothesis? How do we define a hypothesis? In statistical terms, a hypothesis is a statement about the value of a population parameter, meaning, one can make a statement about, say, the true average income of a certain market region, okay? Or one can talk about the true proportion of, say, people in the US who are infected by the coronavirus. Or you may be interested in making a hypothesis about the standard deviation related to the return of a portfolio. As you know, in finance, you can talk about risks of investments or portfolios in terms of variances or standard deviations. So one can, if somebody says, hey, the death rate, for example, 5%, if somebody claims 5% of those infected by the coronavirus are fatal. Okay, so that statement we know is not factual, right? A fact or something that is already known does not necessarily have to be proved. Only statements that are not factual need to be proved, meaning you have to provide evidence in the form of a sample to determine whether that statement or claim, so it can be a statement or a claim, to see if there is evidence supporting the claim. And the evidence that we use here would be the sample. Okay, so are we clear about that? The distinction between a hypothesis and a fact? Okay, a fact is something that does not need to be proved. It's already established. Whereas a hypothesis or a claim is something that is not established as a fact. All right, so at the bottom of this slide, you'll see the 5-step procedure for conducting a hypothesis test or performing hypothesis testing. All right, and so the first step says state the null and alternate hypotheses. Okay, so the question is, what is a null and what is an alternate hypothesis? Okay, so let's go to the next slide that talks about the null and alternate hypotheses. So a null hypothesis is a statement about the value of a population parameter. Again, I will keep stressing this. Oops. I think we'll keep repeating it. It's not necessarily bad. Population parameters such as the mu, proportion, or sigma, and later on there will be more than just these three, developed for the purpose of testing numerical evidence. Okay. The alternate hypothesis is a statement that is accepted if the sample data provide sufficient evidence that the null hypothesis is false. What it tells us is this: the sample data N is used to reject a null hypothesis. Also used to support an alternate hypothesis. Now, some of the characteristics that we need to understand and alternate hypothesis are in the slide. Okay. First, the null hypothesis. Here's how we denote a null hypothesis, and the designation of the alternate hypothesis is H sub 1. Sometimes this is designated, right, or for alternate hypothesis. Either way, H sub 1, H sub A points to or to the alternate hypothesis. Second point, the null and alternate hypothesis are mutually exclusive. Okay, what that means is that it's one or the other. They cannot both happen at the same time. So either the null is true or the alternate is true. And H sub 0 and H sub 1 or H sub A are collectively exhaustive, meaning they are the only two possible outcomes. Either one is true or the other is false, and there are no other options. That's what collectively exhaustive means. Third bullet point, and this is important to know too. The null hypothesis is presumed to be true. All right. Therefore, when you collect sample evidence, it is not to support the null hypothesis, because if it's already presumed to be true, it does not need support. So what we're saying here is that the sample numerical evidence N is used to reject the null hypothesis. Again, it's based on probabilities. All right. Now, in terms of, when you do hypothesis testing, when we perform hypothesis testing to evaluate the null hypothesis, whether we will reject it or we will not, we'll say we don't have enough evidence to reject it. Ultimately, the goal is to come up with a decision, all right, whether to not reject the null hypothesis or to reject the null hypothesis and quote unquote accept the alternate hypothesis. So in this bullet point here, it says that if we conclude do not reject HO, this does not necessarily mean that the null hypothesis is true, okay? But it only suggests that there is not sufficient evidence to reject the null hypothesis. Is that clear? The difference between, when you say that you accept the null, or that the null hypothesis is true, versus the conclusion that we don't have sufficient evidence to reject the null hypothesis. And for problem solving, when you are reading problems, always remember this, all right? That equality is always part of the null hypothesis, whereas the not equal to, the less than, and the greater than are always part of H sub 1, or the alternate hypothesis. Okay, so let's see where, how that applies to the setups for testing the mean of a population. Okay, note this pair of hypotheses. Okay, the equal sign is part of the null hypothesis. The not equal to is part of the alternate hypothesis. Look at this pair of hypotheses. Okay, the equality is part of the alternate hypothesis. The less than is part of the alternate hypothesis. And finally, you have this third pair. Observe that in these three situations, they are both mutually exclusive and also collectively exhaustive. Look at this hypothesis setups for testing the population proportion. Once again, you see the mutually exclusiveness and collectively exhaustiveness of those three pairs of equal to, not equal to, at least, less than, at most, greater than. All right. Now, I said earlier, that why is it important for us to keep an eye on when we are converting problems into hypotheses. Okay, this slide here is important to know. And that when you are doing problem solving in hypothesis testing, watch out for keywords and convert them into symbols, okay? Some of the keywords that you might see in problems include the words improved, better than, as effective as, different from, has changed. Okay, by the way, this list is not exhaustive, meaning there are other ways that words can be used, but these are the common ones. So, for example, somebody uses the word improved. All right, how does this translate? Does this necessarily mean greater than or less than? Well, it depends on the variable that is being measured. Okay, for example, say that you are measuring someone's average score in golf. So X would be defined as the score in the individual scores, game scores, right? So if somebody says, let's say that you are a golfer, and you know that historically you're averaging, say, 100. I'll just say that this is your average score over an 18-hole game, right? Say that you get tired of, you want yourself to improve in this game. So what you do? Well, you take a golf lesson, right? So the question is, after you take this golf lesson, say that it is a 6-week or I don't know, 6-month lesson, did your game improve? Okay. So the question there is, did your game improve? So this word improve, which one does it mean? Which one does it require? Is it this or is it this? Meaning, if you say you play the game 10 times after you have taken this formal lesson, does this question translate to this, or does it translate to this? Which one do you think represent?
Wouldn't it be the first one, because what you're testing should be greater than your original score?
All right. Now the game of golf is, you're better if you have fewer strokes. Unlike baseball or basketball, where the higher the score, the better. In the game of golf, the fewer the strokes, the better.
So it would be less than.
Right. So for this case, the translation of this improve is mu less than 100. So I'm making this example because when you are converting terms such as improved, better than, as effective as, you always go back to the definition of the variable and let that be your guide in terms of converting terms such as improved, better than, or as effective as. Okay? Does that make sense? All right, so maybe let's take a look at some examples before I continue with the concept. We'll go back to these problems. I just want for us to, one, define the same as before. We will define the variable of interest, x, and then what is the population parameter being tested, right? And how do we set up the hypotheses? Okay, so let's start with the first question. What is the variable of interest? X. So a statewide real estate sales agency, Farm Associates, specializes in selling farm property in the state of Nebraska. Its records indicate that the mean selling time of farm property is 90 days. Because of recent drought conditions, the agency believes that the mean selling time is now greater than 90 days. Okay, so before we proceed, let's define X. What is X in this problem?
Mean selling time?
I'm sorry?
Would it be the mean selling time?
That would be the answer to the second part, all right? The mean
Farm property.
selling time. So this is mu, right? After the drought. So this is the unknown value that we will be testing. So let's go back to X. What is X?
The amount of time it takes to sell a farm property.
Amount of time, and this one in days, it takes to sell a property after the drought. Does that make sense? So it's really the same as in chapter 9. So we look at the additional information that is stated. What is 90 in this problem?
Mu.
90 is the mu, correct. And another keyword here, it says the mean time, the mean selling time is now greater. So the agency believes that the mean selling time is now greater than 90 days. So what is missing between mu and 90? What symbol?
Greater sign.
Okay. So that statement translates into this. Now recall that we said as far as the three pairs of hypotheses are concerned, equal to, not equal to, greater than, or this one or that, at most greater than. Okay, so we know that this is part of the alternate hypothesis. So when we set up the hypothesis for here, we will say H sub 1 mu is greater than 90. Okay, so alongside with this, this is the agency's belief. So we set up the null hypothesis, H sub O, which is just the complement of the alternate hypothesis. So that would be this. So we'll say mu less than or equal to 90. Okay. So that's an example of how to set up a null the hypothesis based on what is stated in the problem by when we identify the variable of interest, identifying the parameter of interest, and also looking for the keywords that will be converted into these inequality symbols that you see over here. Okay? Does that make sense so far? All right. So, the next step in hypothesis testing is selecting a level of significance. All right, and in the previous chapter, this level of significance we called the alpha. All right, and the alpha was the difference between 1 minus the confidence level. So alpha is also known as the significance level. As we learned in the previous chapter, alpha is the tail end of the distribution. And tail end, in the confidence interval estimation, we had two tails. But in hypothesis testing, sometimes there will be two tails, sometimes there will only be one tail. So how do we tell whether a test will be two-tailed or one-tailed? Okay, so let me refer you to this slide over here. One-tail versus two-tail tests. This over here is what is known as a two-tailed test. Two-tailed test in the sense that there are two areas of rejection in this distribution. All right. We use this two-tailed test if you are testing that the mean, for example, if you're testing for the mean, is equal to some value. Or the alternate hypothesis would say that mu is not equal to a value. So for two-tailed tests, it is based on the equal and not equal to pair of symbols. This one is known as a left-tailed test. Left-tailed because the area of rejection is on the left side of the distribution. Okay? So whereas in the two-tailed test like this, we divide alpha by 2, just like in the confidence interval estimation chapter. When you are doing a one-tailed test, alpha is not divided by 2. Why? Well, because there is only one area of rejection. It is left-tailed, as I said, because the rejection region is on the left side of the distribution. Now, this one is used when you are testing, for example, you're testing the mean, mu less than a given value. Okay? This must be the complement, mu at least this unknown value. You can also determine the direction of the test, by looking at for some reason I'm not having any luck here. By looking at I'm trying to pick yellow.
Third time's a charm.
I hope so. All right, the eraser is not even working. I mean, the Control Z. I think I'll just leave it at that. Whichever this is pointing to, this one here, it's pointing to the left, right? So we call that the left tail test. For the right tail test, the area of rejection is at the right side of the distribution. So this would take on the alternate hypothesis would be written like this: mu greater than whatever this stated value is. Again, if you look at where this greater than is pointing to, it's pointing to the right. Hence, it's a right tail test. Mu less than or equal to a value. Okay? So are we good so far? All right.
I have a question.
Sure.
Which one do you divide alpha by 2 with?
The two-tailed test over here. We divide this by 2 because there are two areas of rejection. And so the sum of these two is equal to alpha.
Thank
The
you.
significance level. Okay? Is that clear?
Yeah.
Okay, good. Thank you. All right, so let's go back to here now. So we've select a significance level. Usually the significance level will range between, in problem solving here, alpha would range between, say, 0.1 to 0.01. Okay? Most problems that you will see will use as a significance level of 0.5. And later on, I'll explain, what alpha is to be used. If you were doing a hypothesis testing, it is up to you to determine what alpha level is to be used. I'll just explain that further when we talk about the errors, the type 1 and type 2 errors in hypothesis testing. But for now, let's just say that when you are selecting a significance level, that it could range from 0.1 or 10% to 0.01 or 1%. Step 3, identify. Step 3 says identify the test statistic. The test statistic. So what is a test statistic? Is this something that's new? The answer, no, it's not something new, but it is something that we've already covered in the previous chapter, right? So when you are computing the confidence interval estimate for an unknown population mean, we used either the Z distribution, you see here, the Z distribution, or the T distribution. All right, now just kind of from what you recall from the previous chapter. When do we use the Z?
When
When
sigma
it's
is known,
distributed and we know sigma.
Okay, so what was that?
when sigma is known, or when sigma is known,
Okay, when sigma is known, or
if the sample size is greater than 30,
okay, then we may use the Z distribution, right? So when do we use the T? Obviously, this one would be the sort of the complement of the Z is when, say, sigma is not known, and this one says n is less than 30, but we assume that X is normally distributed. Okay, so that's good. And for the population proportion, we just test this to, if the sample size is large enough. That when that is the case, then we can use the z as an approximation to the binomial distribution. All right, so this is something that I will post in Moodle, because I've added this worksheet where I included this slide for hypothesis setup for the mu, right, pertaining to this here, and over here, hypothesis setups for testing a population proportion. All right, so we good so far? Okay, so let's look at, let's go back to the, what was that, the first problem I did? Okay, over here. Continue reading this problem. Tell me which is the test statistic. All right, what do you think applies here? We know we are testing the mean, so going here, testing the mean. Our choices are either the z or the t. What's the sample size in this problem?
100.
100, okay. Is sigma known?
No.
Okay. Sigma is unknown.
We use the z distribution.
You may. So we'll say we will use the t distribution, but may use the z distribution since n is large, meaning greater than 30. All right. So let's see how we can, before we proceed. All right, what is 94 in this problem?
X bar.
Okay, X bar. And how about 22 days? What is 22?
S.
S, right? Good. And then 0.1?
Alpha.
What was that? Alpha, all right? Significance level. All right. So are we clear so far? We've set up the hypotheses. Now, why did we use the greater sign? Well, the key word, as I said, is this. Now greater than 90 days. So that translates into this. Okay? So if we were to draw the distribution that illustrates this problem, here it is. The hypothesized value is equal to 90. All right. On the right side, because this is a two-tailed test, one-tailed, right-tailed, this is alpha, which is the 0.1 over here. Corresponding to this point, such that the area beyond this point is equal to 0.1, what is the z-value? How do we obtain the z-value? When the area beyond this point, it's shaded in yellow, is equal to 0.1.
You find the inverse norm.
Okay, the function in Excel was norm.s.inv. And what number should I put inside the parentheses?
0.9.
Correct. All right, so let's do that. Equals norm.s.inv 0.9 gives a z-value of positive 1.281552. Now, the term that is used for this number in hypothesis testing, this is known as the critical value. Critical value. Okay? So the question is, what is a critical value? Definition of a critical value. A critical value is a point along the horizontal axis that represents the boundary between the reject HO region and the fail to reject the null hypothesis region. All right. So where are these two regions in this distribution? The yellow shaded area is known as the reject HO region. Whereas the area to the left of 1.2815552, this is known as the fail to reject HO region. Okay, we clear so far?
Quick question, Professor. For the norm S inverse function, why do you use 0.9 as opposed to 0.1?
Well, because if you use 0.1, then you're looking at the z-score on this left side. Remember that the norm inverse is a cumulative, meaning it's cumulative from the left all the way to a given z-score.
Oh, I see. Okay.
Okay, so you know, if you use the 0.1, you'll get a negative 1.281. All right.
Gotcha. Okay. Thank you.
All right. So adding to this, I defined the critical value as the point along the horizontal axis that represents this boundary between these two regions. What this is also used is we compare what is known as a computed statistic. Okay, so what is a computed statistic? Computed statistic is a number or statistic that is derived or computed from sample data, meaning it's based on n. All right, so let's go back to say this slide here. So we have this hypothesis, right? This number, this line, you see this? It says reject HO if. This is what we call the decision rule. The decision rule when you will reject the null hypothesis. So the decision rule is comparing what is the computed statistic, which is this, and that is based on this formula or this formula, right? Remember that I defined computed statistic as it is derived or computed from sample data. So when you compute, when you are comparing a computed statistic to the critical statistic over here. So this side is known as the critical statistic. When you're comparing the computed statistic to a critical statistic, essentially what you are doing is trying to figure out where that computed statistic is in relation to this critical value, all right? So for example, if the resulting computed statistic based on the sample data is 1.0, okay? Just as an example. Where is 1.0 in this distribution? Well, 1.0 was probably over here, right? Say that is your computed statistic. This computed statistic lies inside the fail to reject HO region. Therefore, if we carried out this test and it yielded a computed statistic of 1, we will conclude to fail to reject the null hypothesis. Okay? Let me erase this because this is not really, I don't think that's the z-score for if we carry out this test to completion. All right, so we're good so far? All right. So what is the decision rule? Based on this. Remember that for that particular problem, here's the applicable decision rule. All right, so we will reject HO if Z or T, the computed Z or the computed T, is greater than the critical Z or critical T. Since we have a large enough sample, we can use in this example, we can use the formula Z X bar minus mu over sigma over the square root of n. But remember that because n is at least 30, and if we are using the Z formula to compute the test statistic, that it's okay for us to substitute in its place. In place of this, we will use S. Okay? So let's substitute the given information into the formula. X bar was 94. The mu, the hypothesized mean, is 90. S the sample standard deviation is 22 over the square root of 100. Okay, computing that value is equal to 94 minus 90 divided by SQRT, oops, 22 divided by SQRT of 100. Okay, so I just translated this equation into an Excel equation so I can compute the z-score. So what do we call this?
The computed value?
Okay. The computed value or computed statistic. Good. Where is the computed value with respect to the critical value? Remember, here's your critical value. Where is 1.818? Going this way? Is it below?
It's so it's inside of alpha because it's greater than the 1.28. Because
Okay.
it's like 3.
Right.
'cause it's not considered.
Right. So this is 1.818. So looking at this decision rule, is 1.818 greater than 1.28152? You know, is this relationship true? The answer is yes. Therefore, the conclusion would be the null hypothesis can be rejected based on sample data. All right. This is what we call as the statistical definition or conclusion. In response to the question, has there been an increase in selling time? All right. Does that make sense for this whole problem? Any questions? All right. So we solved this by hand. Now let's take a look at the solution to this same problem using the template and see how quicker can we solve the same problem.
So I forgot to tell you something, Renee.
Sure.
During our review, we decided we'd like to rename the template to the Oracle.
Oracle. What is the rationale for that?
That way, whenever we have to solve a problem, we consult the Oracle.
All right. All right. So you will find the templates for Oracle, according to Doug, for testing one population. Okay. Testing the mean. So for this problem, we used the z-test. So let's solve the same problem using the z-test, and then we'll redo it using the t-test and compare the results. Okay, so here's how you fill this template. What was the hypothesized mean based on how you set it up in this problem here? So let this be your guide. Was 90, wasn't it? Now, this part is important too, because look, it says mu equal to 90, mu not equal to 90. But the way we set this up was this was a greater than test. So we need to change the code for the direction of test. It says enter 1 for two-tailed test, 2 for right-tailed test. So we'll put 2 there. And then sample mean was 94. The sample standard deviation, which we used as an approximation to the population standard deviation, 22. The sample size of 100. And then the significance level of 0.1. Okay, so you see here in this output, just going to copy this, paste that down here. All right. Here's the critical value, and here's the computed value. So in this output, you'll see the computed value inside the reject HO region. So we arrived at, using the template, you should arrive at the same conclusion. That is, the null hypothesis can be rejected, and then that we will conclude that the selling time has increased based on the sample data. Now let's resolve this problem using the t-distribution this time. So I'm going to select this option, and hypothesized mean is still 90. Direction of test is 2. The sample mean 94. Sample standard deviation 22. Sample size 100. And significance level 0.1. Here's the output. Note how closely both the computed statistic and the critical statistic are to these two numbers. All right, are we good? Are you okay? All right, so let's take a 5-minute break. Then when we come back, we'll continue with with the concept and align those concepts with problems. And while we are on a break, I'm going to link this to Moodle. So I'll be back here by, say it's 2:44, 2:45. Let's back by 2:50. Okay, so let's take a look at exercise 1031. 1031. And the problem states that a new weight watching company, Weight Reducers International, advertises that those who join will lose, on average, 10 pounds in the first 2 weeks with a standard deviation of 2.8 pounds. A random sample of 50 people who joined the new weight reduction program revealed that the mean loss to be 9 pounds. At the 0.05 level of significance, can we conclude that those joining weight reducers on average will lose less than 10 pounds? Okay, so let's look at the important keywords here. Based on the question, can we conclude that those joining weight reducers on average, okay? So we're talking about the mu. We lose less than 10 pounds. Translated, less than 30. Okay, so this is a test for the mean. Before we proceed, let's answer the following questions. X, what is the variable of interest here? Isn't it the amount of weight lost by those who join the program? All right, and X is a continuous number. What is the population parameter being tested? We said it is the population mean, mu. And how do we set up the hypotheses for this problem? We already set this up partially.
Where did the 30 come from?
Good question. It didn't come from anywhere. From my imagination. And thank you. All right. So, mu less than 10. This is the question. And then H1. So this would be weight reducers international claim. All right. So question as far as what is the appropriate test statistic for carrying out the test? Question is sigma known? Yes or no?
Yes, it's
Yeah.
Okay, where is that? Where do you see that?
2.8 pounds.
Okay. So sigma is equal to 2.8 pounds, right? N, what's the sample size?
50.
Okay, so by these, we will be using the Z distribution. All right. Now the decision rule will be to, since we are using, I'm looking for my snipping tool. This one here. Okay. So if we draw the distribution and determine where the rejection region is, here's the hypothesized average of 10, and this is a left tail test. Therefore, the area of rejection is on the left side of this distribution. So we will obtain the critical Z. To obtain the critical Z, we will need the alpha, which is 0.05. Okay, so in here, we will use the norm.s.inv, and this time we will use the 0.05, not 0.95, right? So this is the critical Z value. Okay. We can compute the computed Z by hand if you want to. So by hand, it will be what was X bar from the problem?
9.
9, thank you. N of 50, sigma of 2.8. So we can compute Z as equals 9 minus 10 divided by 2.8 divided by the square root of 50. There's the computed Z, which is computed Z is over here. All right. So since the computed Z is less than the critical Z, in other words, it is inside the reject HO region, the null hypothesis will be rejected. And by rejecting the null hypothesis, we will say that the data, the sample data, does not support the weight reduction international's claim.
Yes, it does, because the Z value is within the critical value. So there's enough evidence to reject the null, which means that it does support that you.
Yeah, so I got it, got deleted. Well, here, what was the weight reductions claim? The claim is this, right? That on average 10 pounds the first 2 weeks. But by rejecting the null hypothesis, we're saying this. The mean is less than 10. Right, Iridian?
Yeah, got it.
Huh?
I got it. I just got the claim wrong, and so
Yeah.
since we saw it within the critical, within that area, I assumed that it was going to be that.
Okay. So the data does not support Weight Reduction International's claim that the average weight loss is 10 pounds on average. Okay. The data supports the contention that the average weight loss by participants is less than 10. Okay. So are we clear so far? Am I making sense here?
More or less.
More or less. So what's the less part, Chris?
Oh no, you're fine. I was kidding.
All right. Okay, good. So let's solve this problem using the template. We'll be using the test involving the mean, using the z-test. Okay, so the hypothesized mean is 10. Direction of test, it's left tail, so we'll put 3 here. The sample mean is 9. The standard deviation, sigma, 2.8. Sample size, 50. And significance level, I believe it was 0.05. Okay, so paste that there. So since we concluded that the average weight loss is less than 10 pounds. Now, if you were asked, what is the 95% interval for the true mean weight lost by the participants in this program? Let me type that up. What is the 95% interval estimate of the true average weights lost by participants in this program?
Are you asking for the margin of error?
No, not the margin of error, the confidence interval estimate. Which the margin of error is a component of that.
So you have it on the screen though? I mean, the 95% confidence interval, you have the upper and the lower limit right there.
It's right there, right? Right here, right? So we can say that the interval 9.8 and 8.2 contains the true mean weight lost by participants in this program. So it's some improvement, So the average weight loss is between 8.2 and 9.8 pounds. So that's the 95% confidence interval for you. Okay? So does that make sense so far? It's the same, concept that we carried on from chapter 9. Any questions?
Really quick, can you go over again how you determine if it's a left tail or right tail test?
Oh, okay, yeah. It's based on the if you just look at the the alternate hypothesis. So if it's if the alternate hypothesis is greater than, meaning it's pointing to the right, it's a right tail test. If the alternate hypothesis is pointing to the left, it's a left tail test. Or if it's equal to, not equal to, it's a two-tail test.
Okay, simple enough.
Yep. Okay. Any other questions? Because I know I owe you some 6 minutes from last time, so I'm going to give those back to you today.